Okay, let's go ahead and get started. It's a great pleasure to welcome Willem Visser here to UW to give a talk. He is one of the leading lights in doing symbolic model checking of software. At the time that he was working on this, nobody believed it was actually going to work, and he showed them that was wrong. He's done a tremendous amount of work since then, also on symbolic execution. So he's going to be talking to us today about testing. Thanks.
Thank you. I think whoever was wondering about whether these things were correct or not, they were probably right. I'm still not sure it actually works, but let's leave it at that, I guess. Okay, so today's talk is going to be not so much about how we do these things, a little bit more about some applications of symbolic execution, model counting, all of the above, all running on a suite of tools that we've been developing for close on 20 years now. So it's been a while. Okay, so the idea of today's talk is to talk about these things, like mutations. And specifically, I want to look at mutations somewhat in the context of fault seeding, because as you might know in software engineering and maybe even related topics, there's a big move towards, I want to show how good my super duper new tool is, but I'm solving this immensely important problem, but I don't actually have any examples of bugs in this domain, so let's just invent some. And that's pretty much what mutations are being used for these days a lot in software engineering. And I was intrigued by the question of how hard is it actually to detect these mutations, or in the terminology of mutation testing, to kill them. So this talk is all about that, and then at the end I'm going to throw something in about coverage as well. Okay, so mutation testing 101, for in case you don't know. The way this typically plays out is you have some program, and in this program you have, let's say, an equality check at some point. Now, what you do next is you have something called a mutation operator, and you take your original program and you mutate it, like here, for example, in the 6 possible or 5 possible ways that you can change a relational operator. And now you have 5 new versions of your program. And the whole idea at this point is to, well, you call these your mutations, and now you want to see whether you can actually detect these mutations with some tool, let's call it X for the moment. So let's say we run these 5 versions, and we look at their outputs and see if it differs from the one that we had originally. That's, or at least that one way to view it. And let's say this one failed or whatever. And, well, or let's say here you didn't find the difference between the original version and what you have now. And then these tick marks are all cases in which you did find a difference between what you had before and what you have now. So what is X typically? In the original work, X is the reference version's test suite. So the intuition behind mutation testing is pretty good. What you have is you have your original program, and you have your test suite. And what you really want to know is how good is this test suite. So what do? You take your original program and you break it on purpose. If you break it on purpose, then in theory, your test suite should at least find out that you broke it, right? So that's the whole idea behind mutations. Now, of course, the other thing is sometimes it's also my cool new bug finding tool, which is now the scenario in which you use it for fault seeding. And there's this little question about what's the relationship between mutations and real bugs, but that's not really going to be the focus of this presentation. Okay, so testing 101. Here you have some input, some oracle, i.e. some criteria that you decide on whether this input passes or not. And you obviously want it to pass, and you usually have a whole bunch of these, and that's called a test suite, right? So you have your M tests here, and you run them to see if they pass. Now, when are you happy with your testing? What's your test adequacy? Usually, it's some form of coverage, typically, and that coverage can be of the code, so like structural coverage of the program, or it checks that all the requirements is covered by your oracle, right? So this is typically what you do. Now in mutation testing, it's a little bit different. Here you take just say the first test, so test 1, and you run that over all the versions of the program you just created, and you check your oracle. So oracle 1, so you input 1, oracle 1, that stays the same. You look at all the different versions. And let's say what you find here is that in this version, the test failed, whereas in these two versions, the test passed. Then you say the mutation is killed if there exists a test that fails on it. So this mutation, the one that generated the second piece of code here, it will be considered to be killed because there's one test that fails on it. So if you run your whole test suite, you would very much like to hope that all of the mutations are being killed by your testing. And there's something called the mutation score, which is the number of killed tests over your total number of mutations. You want this to be 1 ideally, but of course for various reasons it isn't 1. Okay, so the elephant in the room, of course, is whether mutations are the same as real errors. We don't care about that, but let's just assume the answer is yes, which a lot of people assume. What you then want to, well, one other use then for mutations is to seed faults. So create some fake faults, basically, or real faults, whatever, depending on how you feel about it. And then you want to see how good is your tool that you just developed, your new bug finding technique or whatever. You want to know how good it is at finding these faults that you just seeded. So the question then is, how hard is it to kill such a mutant? How hard is it to detect a mutant? Now, in previous work, most people fix the test suites that you do this over. What we want to do is look at all inputs. And we would ideally not want to care about the oracle either, but as it turns out, you do have to care about the oracle. So I'm going to use 2 oracles, one good one and one bad one, and later on I'll show you what I mean by good and bad. But it basically means how precise is it? How good is it at detecting that something actually is wrong with your program? But maybe this one here, the all input, it might sound a bit like a bridge too far to look at all inputs, but hopefully I'll convince you that at least in some settings you can do that. Okay, so the question is, how hard is it to kill a mutant? Spoiler alert, turns out it's not all that hard to kill mutants. And what is in fact the case that where this mutant is born, i.e. where it's seeded, is a little bit more important than whether it's a chicken or a bull that you're trying to do something with. So how do we do this? We look at the percentage of inputs on which the reference version and the mutated version gives different outputs, or the same outputs, depending on how you think about it. Okay, that's how we're going to do it. Now, let's look at a little example. So let's say you have this green program here. This is your original program. So all it does is it says less or equal to j. It returns true. And notice that I also give it some range here in values. And the reason why I do that is simply so that the numbers I'm going to show you next make some kind of sense. But in theory, you don't actually need to necessarily give it ranges, because min-int and max-int is always there as a backup range. But I tend to put little smaller ranges just so that the numbers seem more sensible. OK, so here's a program, less or equal to j. Here are the 5 mutations you can do, which is pretty much the 5 mutations I showed you on one of the first slides. So these 5. So the first question would be, which of these programs do you consider the most broken? I.e. would give a different result on the largest number of inputs.
The first one.
Yep, it is 100% killed. So meaning that 100% of the inputs will actually give you a different answer in this one. And of course, the one at the bottom is the least likely. And in the ones in the middle, this one is pretty likely. These two, if I had some wine or beer to offer at this point, I would love to give you a prize for how much you think they would be different. But it's not at all obvious what they will do. But as it turns out, they're all hovering around 50%. So about 50% of the inputs will show a difference in those two cases. And every time I kind of create a new slide on this kind of stuff, I always literally run the tool to tell me what these numbers are, because I can never work it out by hand. It's remarkably difficult. Some cases not that difficult, like the first and the last one, but some of the others are a bit more difficult. OK, so we do mutations at the bytecode level, right? So if you look at the original, this is the program, that little program there. This is the bytecodes, Java bytecodes for it. And I'm just highlighting 2 cases here, integer constant 1 and 0, which is like the true and the false that it's going to be returning. We could also have mutated that, right? So if you mutate the true and the false return for this method, you kind of intuitively think, surely, if I change the true and false, then that's going to be like 100% killed, right? It just feels that it should be like that. Unfortunately, as it turns out, these two are also about 50% each roughly killed, and not 100% as you would have expected. So what?
Changing 1 to 0 and 0 to 1, or changing them to 22?
No, 1 to 0 and 0 to 1. Yeah. And okay, so why is this? The reason for this is actually obvious, but maybe not at first sight, and that is that not all the values reach these points where the mutation is, right? So if you look at simply the amount of inputs that will show a differing result, you get these 50% numbers. But if you look at the number of inputs that actually reach the point where the mutation is, of course, it's 100% killed. So if you reach there, any value that reach there will, in fact, show a difference in the output. Okay. So one of the things we are going to do is we'll be controlling for how hard it is to reach the point of the mutation. So all we do there is we just can figure out with the technology I'll show you in a second exactly how many values actually reach the point where you're going to make the change. So therefore, you can just use that as the denominator and not the complete input space of the variables. We make one assumption, and that's you know nothing about the input distributions of the program. So you assume it's completely arbitrary. That is not a serious constraint. We can easily change it. But for purposes of the presentation and stuff, I'm just going to stick with it because it makes things a lot easier to explain. And we are going to focus on programs that the hammer we have can actually hit. So that would mean you can do symbolic execution of it, and also you can do model counting for this. And I will explain what both of these are in the next few slides. So here's an example of a little program that you want to analyze. And let's say we're going to do symbolic execution here. Program says for some x and y, if x is so y is equal to 10x, then you reach some statement S0. It doesn't matter what S0 does as long as it doesn't do anything with side effects. So let's just say it prints out something or whatever. Else S1, and then there's another if here with some other constraint, and then you reach S2 and S3 depending on which ones you get. So now in symbolic execution, you start off with symbolic inputs, obviously. So x and y, big X and big Y, that is symbolic. And the little bit between the square brackets is referred to as the path condition. And what this is the constraint under which you reach this point in the code. So constraint on the inputs that reaches this point. So here you have no constraints whatsoever, so anything can reach the beginning. But if we reach S0, you can only get there if your input Y is 10 times your input X. Right, so that's a constraint. Now in symbolic execution, one other thing you do at this point, of course, is to check that that's feasible. But in this example, everything is going to be feasible. If it wasn't feasible, you basically chop off that branch in the analysis and you forget about it. Okay, so from S0, you can go to S2. And now you can join whatever you had here with whatever constraint you have here. And if the combination of that is still true, you can reach S2. Similarly, you could have gone down to S3, so from S0 to S3. And similarly, on the other side of the thing, you could have gone to S1 first and then to S2 and S3. And this little tree you end up here with is like the symbolic execution tree that you can now do all kinds of funky things with. And the most likely thing you're going to do at this point is you're going to generate tests. So you solve for these leaves, for example, and like the solution might be x equals 1 and y equals 10. And if you execute that, you're going to run down that path. It's the classic thing you use symbolic execution for. Now, what we're going to do is more something like this. So this is the exact same program, with the exception that we now have these, like, it looks a little bit like a river of values that's flowing down here. Remember, we had 99, 0, 99. Actually, we didn't have it here, but here we have 0 to 99. So that gives you 10,000 values that flow in at the top. And out of that 10,000, only 10 of them come this way, because that's the case where y equals 10x. And the other 9,990 goes the other direction. And similarly, there's another split here at the bottom. Now, basically, what are we actually doing here? We are calculating the number of solutions for these constraints at the end here. And that's like referred to as model counting. And oftentimes, we use a tool called Latte to do this model counting. It's off the shelf from my perspective, so I have no real idea what's in the bowels of this system, except that it counts the solution for a conjunction of linear inequalities, and it does it reasonably fast. Nowadays, we use a different one called Barvinock, which is even better, but we just use this technology. So we feed it a path condition, and it spits out a number that comes back. The most important thing is that that number is not or the time it takes to calculate that number is not dependent on the size of the input domain. So here I had 0 to 99, for example. I could have made it min into max int. It would have taken the same amount of time. The reason for that is it actually comes up with a characterizing function for that value, so you can actually plug in any ranges that you want to do. But for us, this is all now black box usage. We do symbolic execution and we calculate these numbers. And ultimately, these numbers are now going to be of some use to us, because you can imagine if I know that 6 values comes this way and 4 goes this way, I already know the conditional probability at this point is 60% versus 40%, right, for this value. And I also know that, say, 6 over 10,000 is a relatively small number, so the probability of an input coming all the way down this way is very low. Sure?
Just to clarify, you said for simplicity we were going to not know the probabilities of reaching a point. It's with what you just said, it sounds like for simplicity we're going to assume a uniform distribution of inputs. That's what you can layer on any other distribution.
Okay. Yeah, exactly. I mean, correct. It's not that I'm not using a distribution, it's just like taking the uniform distribution. So we can in fact plug in any distribution, and you can think of it as splitting this branch here with a few more options and stuff. So it just makes calculations a bit more cumbersome, but it can be done. It does have to be discrete. Okay, so here's the process I'm going to follow now. Remember, the end goal here is we want to calculate the number of inputs on which a reference version and a mutated version gives you a different result. So for every program we analyze, we create this little harness here. It itself, like the check program there, takes symbolic inputs, A, B, C. And it'll take the same inputs as whatever the program is you're interested in. And here I'm assuming whatever you're interested in is just going to return some value. And ultimately, I'm checking that the reference version and the mutated version gives the same answer. Okay? And for every path condition on which it does not give the same answer, I basically just count how many solutions there are, add it up, divide by the total domain size, and that gives me the percentage difference. Reason why this works is in symbolic execution, all paths are by definition independent, so you can just add them up at the end. And then there are two definitions we'll be using. In mutation testing, people are always very interested in this notion of equivalence or equivalent mutants, because in theory you can create whatever mutation of your original program, but it can in fact be the do exactly the same thing as the original version, which then by definition means you can't kill it, which is kind of an inconvenience. Here we can calculate that very precisely, and it's if the difference is 0%. And then we have, if it's less than some small threshold, then we call it stubborn or hard to kill. So if a very small percentage of the input space shows a difference, it's a mutant that's going to be hard to kill. So that's ultimately what we're going to be interested in, this notion of it's hard to kill. Okay, so I'll kind of skip this slide. We implemented it on JPF, which is, well, SPF, Symbolic Pathfinder, which itself is an extension of Java Pathfinder. We use caching to make this go faster. The important thing is I have a Docker file that does all of this stuff. If you want it, I can just send it to you. You'll have to go and have a coffee or free for it to build the image of the Docker image. But point is, at the end of that, you can press a button and repeat all the experiments that I have here. Now, we're going to be comparing with a paper that basically does what we're doing here by hand. And it's just for interest's sake in some sense. We did this work, and then I discovered this paper, and then we went back and picked some of the examples up from this paper just for comparison. Essentially, this is ICSI 2014. Looking at equivalent and stubborn mutation operators, but analyzing it by hand to see whether they are stubborn or not. Okay, what we did was we picked two of the examples. These are smallish things like the triangle classification problem and TCAS. We do bytecode mutation and not source code mutation. They have more operators. We have some subset of that, but it's fairly easy to compare. We use what's called strong mutation, which means that you only look at the end of the program, whether it gives a different result than the original program. There's also weak mutation, which basically means right there where you made the change, does that make a difference? Which, of course, in almost all cases, it will make a difference. We consider a mutant to be stubborn if less than 0.1% of the inputs shows a difference. In this other paper, they considered a mutant to be stubborn if you have a test suite that gives you branch coverage, but it does not kill the mutant. And of course, by definition, then it's also not equivalent. So all of this, the not equivalent bit they did by hand, but then if they considered it not to be equivalent, and it wasn't killed by any of their tests, then they considered it to be stubborn. Okay, so here are some of the examples. I'm just flashing this up so that you can see it, but this is what we call version 1 of the triangle classification. This is version 2. The only interesting thing here is this is much smaller, shorter version of the problem. That's going to be relevant to at least one of the results. And this is version 3, which we also refer to by the initials of the other paper's authors, because this is actually the version of the triangle classification that they use in their paper. And what's interesting about this version is it doesn't actually solve the triangle classification problem. Now, note this is not important for their paper, because in their paper they were really interested in just comparing. This was their reference version, so it doesn't really matter that it doesn't actually solve the problem. It did give me a few extra gray hair, because I compared it against my oracle and it gave the wrong results, and that kind of made me think that there was something wrong in the tool, but actually it's just because this is not correct. Okay, so here are some of the results we got from analyzing this. When it says YHJ, it means it's the result from the other paper. When it says version 3, it means it's running the same thing through our tool. So the first thing to notice is that we find 2 less equivalent mutants than they did. And it turns out that the 2 extra ones they found, it was just a mistake. Remember, they did it by hand, and it's hard to tell whether things are equivalent or not equivalent. And they thought it was equivalent, but there were some very subtle inputs you could give, and it would show that it wasn't equivalent. With the TCAS example, we do not have the same number of mutations, which also seems like something that's a bit bizarre. It turns out that in their case, there were like 2 lines in the code which they, for some reason, just didn't do any mutations. All their stuff is on the web, so it was really nice for me to go and be able to check it. And similarly, unfortunately, those 2 lines that never mutated is also the 2 lines on which there are 2 extra equivalent mutants, which they didn't have because they never seem to have mutated those ones.
There was no difference due to source code versus bytecode?
No, but I basically lifted some results and so on to make it comparable as well. So, but no. Not really. Anyway, not on these ones. There's going to be some down here where there is actually a subtle difference. Here is the case where we had the 2 versions of the triangle classification. The second one, you might remember, had less source code in it, basically. So obviously, if it has less code, it's going to have less mutations. But notice, less mutations. There were still more stubborn mutants in this first one. But the number of equivalent mutants was the same, so they solved the same problem.
So how do you deal with if the mutated test case actually crashes or not return anything? So
okay, so that didn't happen in this case, but how the test harness would have needed to be just adapted slightly. So if the one returns a result and already knows it returns a perfectly valid result, then if the second one throws an exception, if the reference version doesn't throw an exception and the mutated version does throw an exception, I consider that to be different. And then I would do the calculation of why is it different. I look at the path condition on which the one crashes and the one doesn't. Okay, and then the last one is just, here I needed to do a bit of manual work because they made a special case of logical connector operators because they found them to be particularly good. So that's ands and ors. So like if you have x greater than 5 and z less than 10 or whatever, something like that with an and in it. Now, of course, in bytecode, you do not have those because they compile out. So I had to just by hand go up and lift them back up to the same level so that I can do this comparison. So it turns out that we got very similar results. It's just, again, here is a small difference with the stubborn mutants because my definition of stubborn is 0.1% or whatever. Their definition of stubborn is it's not killed by the test suite. So obviously, those are not apples to apples comparison, so it's slightly different. Okay, but now for the...
I have a question. Can you go back? You have the big red rectangle.
This one, yeah.
With the 2 6s at the far right.
Mm-hmm.
It seems like the fact that those are the same is totally a coincidence. They really have nothing to do with one another.
That's a good that's a good question. Could be.
Okay.
It could be. I will argue, but without any strong evidence, that it is a better chance that this would be the same than this would be the same. I.e., if you're solving the same problem, there is a slightly better chance that the equivalence would be related rather than the stubbornness. And I'm going to try and argue that again later.
Are those the same 6 test cases?
Are those the same 6 test cases? Is a good question. Well, you know, it's hard to define, right? Because it's different programs, and we're talking here about mutations. So it's, I think actually,
move on.
Actually, in this case, I think it is because it's right in the beginning in the first line of the code where it throws out all the negative values and stuff, and it has something to do with that. Yeah, but good question anyway. This will come up again slightly. Okay, so but now to the interesting stuff. That was all kind of like just comparing doing something automatically versus doing it by hand is obviously not quite the same. Okay, but we saw something much more interesting in the data, and here basically is the gist of it. If you take the original program again, the first one, the big version, we basically found that there was this point in the program which we called the stubborn barrier, and the reason for that is everything beyond this point was pretty hard to kill, and everything above this program was not really that hard to kill. Why would you think that is?
So maybe there are no more operations being done. The ones early, changes early in the program tend to cascade and cause problems later, whereas ones late don't have any other computations to muck up.
I'm going to go with no. The reason is simpler. The reason is only 3% of the inputs actually pass this point in the program, because there's a return statement here that basically gobbles up most of the program inputs.
Does stubbornness not have to do with the percentage that are covered?
So I am now going to introduce that definition. Oh. Up to this point, it didn't. Up to this point, it was just how hard it is to kill. Yeah. Okay, so that, you can see how that could have confused you. Yeah, but the bottom line is very few of the inputs actually got here, so any change here by definition was hard to cover. But now let's introduce the same results, but this time looking at it from the perspective of controlling for the reachability of the data. Okay, so everything on the left-hand side of the dark bar here is, well, I mean, this stubborn column here is not looking at whether you reached it or not. It's just the blind results from before. Whereas everything on the right-hand side does look at, it controls for how many values actually reach there. So now you can see, I call this really as in really stubborn. So this is just stubborn. That's really stubborn because it actually is still stubborn after you controlled for reaching it. And you can see from these triangle examples, there's basically nothing there. It was for TCAS, there were a few there. But then the more alarming column should be the two on the right. This one says if you reach it, you always kill it. So how many of them are there? Like 4 out of 5 here, and a reasonable proportion of these others as well. And in restricting that or relaxing that slightly, I give it like a 1 in 3 chance. Like if you reach it, you have about a 1 in 3 chance of killing it. That's the column at the right. So that I can refer to as easy to kill. So what should be slightly disturbing here is that this seems to be rather high, right? So if you can reach it, you can kill it for this class of operator. And what we looked at here is arithmetic and constant replacement. But that's maybe not so interesting. What's more interesting is if you look at relational operators, because this is typically the stuff people consider to be a useful operator to use for mutations. So here, there are not that many that you always kill, but this number here, that's still remarkably high. So basically what this is all saying is that if you don't look at how hard it is to reach the point in the code, then actually mutations are pretty easy to kill. So if you can reach it, you have a good chance of killing it. There's a little bit of good news, and that is that not all mutation operators are the same. And if you look at this ugly chart, which I will abstract for you in a second, there's a big divide, again, with this line. Above this line is a bunch of red numbers here. What this means, everything that's above the line is if the always killed percentage is greater than 20%. And here is if it's still stubborn after you've looked at reachability, with at least more than 20% of the cases we see this specific operator, then it's in the green bunch below. So the red bunch is negation operators, with the exception of this one. This one snuck in there, so I don't know why that is. It's just by accident, I guess. But it's probably the exception that shows the rule, hopefully. But these are all the ones where you're unequal to equal, less than to greater equal. It's where you just apply a negation to the thing. So if values flow down this way and you direct them all to go down that way, that's when they're easier to kill, right? And that should obviously be somewhat close to common sense. And these ones at the bottom, they're all the off by 1 cases. So if you have less go to less to equal, then it's harder to kill. Okay? Should be very, very obvious.
And that's hard to kill, even accounting for coverage.
Yeah, even accounting for coverage. It's because it makes a very small little change in the flow of the values. Okay, so just looking at this, if you are interested in having hard to kill mutants, focus on these off by 1 ones rather than the other ones. Okay, but the bad news is it turns out that there is another small snag. What we have seen so far are cases where it is very easy to distinguish whether the result is different from one program to the other, right? So the oracle was very precise. Now the problem is what happens if the oracle is not that precise. So here is an example we're going to look at. It's a binary tree. As it turns out, I have had a binary tree code in my example set since 2004 that had not 1 but 2 bugs in it. The first bug was kind of obvious and it wasn't that interesting, but the second bug was kind of severe. And for some reason, because we were doing test case generation and never bothered to check that whatever the test cases is we would run will actually do the right thing, we've had this example forever with these bugs in it. So this is my binary tree example. So this is a real bug in some sense because it wasn't introduced. So on the left-hand side, we're going to use what's called the repo K usually, which is the representation invariant. So basically, this is this thing structurally a binary tree or not? That's what it says. And on the right-hand side, I first check if it's structurally OK. But if it is structurally OK, I basically go and build up a string that contains all the values in the exact order in the binary tree. So that's a quite a bit more precise oracle. So these are going to be the 2 I'm going to be using. So now here's the data we see. So it's linearized versus repo K for the binary search tree. These are all operators, arithmetic and constant replacement, relational operators, and this is that special class of negation operators that we saw before are usually not terribly good because they are too easy to kill. Okay, so what we see here is that if you have, if you look at equivalence and you look at linearization, which is now the precise precise oracle, then you will see that actually you find more equivalent mutants if you have the less precise oracle, right? So that should be fairly easy to see. My analogy is usually my eyesight because I don't have very good eyesight, so if I see 2 things in the distance, they kind of look the same. So and people with better eyesight might be able to spot the small differences between them and therefore will have less equivalent mutants. And these two, the easy and the always cases are of course related basically, so they both have the same characteristic. So if you have a more precise oracle, then you see that it is in fact going to have more easy to kill and always killed mutants because it can more accurately show the difference, right? So precise oracle less equivalent but more easily killed. Imprecise oracle more equivalent but less easily killed, right? So the snag here, of course, is you would say, gee whiz, really? That's surprising. Not, right? It should be blatantly obvious. Except that it is maybe not that blatantly obvious, and I'm going to cite a paper from this fine establishment. It's not negative on you, actually, so don't worry. Here's some text I pull out here. It says, we found that real faults were more often coupled to mutants generated by conditional operators and relational replacement. I highlighted that in yellow because those 2 classes is also in my data, but statement addition is not in my data, so therefore I didn't pull that out. And in a paragraph or so later, it says, none of these 3 mutation operators is known to generate a disproportionate number of equivalent mutants. Cite 40. 40 is this paper I'm comparing with in my data, right? So all I'm saying is, I hope I just convinced you in the previous slide that the oracle is really the important thing when it comes to whether things are equivalent or not. And that paper basically got that result wrong, but you guys say, yeah, no, that's how it goes. So I'm just saying it might seem dead obvious when I put it like this, but it isn't necessarily that obvious. So if we look at the outcomes of this other paper, they said they found this relational operator class get stubborn and equivalent mutants in about the same amounts. Logical connector they found to be really good. And they found that more mutations implied more equivalent mutations. And basically what I'm arguing is that pretty much all of that was an accident of the test cases that they were considering, because equivalence depends on the oracle more than anything else, and stubbornness depends on, remember, the location, which most people don't consider, the oracle, and not just the operated class, so whether it's relational or not relational, it actually even depends on the exact things inside of the operator that you're looking at.
So those in order of importance?
No.
Or are those just a list of the
That's
things?
just 3 things I pulled out. There was a time when I had this slide with little tick marks and crosses on it because of the things that I thought looked the same, but then I realized that I was wrong. So now it has the red box on it. But my bottom line of this is just simply that be careful when you do this empirical stuff, because it is not always the thing you think you're studying might have some other things in it that, that could be influencing you a little bit more than you might be realizing. Okay, so one thing I just quickly wanted to mention is, of course, you're going to say, oh, look, but you have these programs that's like you fit on one slide, right? It surely can't be representative of the real world, so I created this slide. So small programs, yes, sure, small programs, but we look at all the inputs, which is something that is important, I think. But then let's take a larger program. So what would the larger program do? It is likely to have more branches. So the dotted green line means likely to be the case. So it's likely to have more branches in the code.
You mean in the absolute sense?
Yeah.
Per line of code,
absolute
the same
sense.
number.
Absolute sense, yeah.
Right.
I mean, more branches, right? And what does more branches mean? It means basically less values will flow down these branches. Now, not always, but in most cases. And the reason for that is that every time you have a branch, you add a conjunct, which restricts the flow of the values down the path. Of course, if you merge again, I can see Mike is ready to jump on me for this. When you merge again after an if, for example, they will come back again. That's true. But you oftentimes have the situation that if you have more branches, you will have, at least for that portion of the if statement, you're going to have less values flow there. Now, if you have...
When you I'm not going to jump at you. When you say less value, do you mean as a proportion?
Actually, literally,
relative or absolute?
I actually mean absolute or relative. It doesn't really, well, definitely absolute. Because every time there's a branch in the code, some values get diverted this way and some goes this way. So by definition, after every conditional, you have less values that flow down that specific path in the code. Always.
So in some sense, it's almost more that you have more paths than more branches.
Sure, yeah. I mean, the more I could have said more paths for sure. Yeah, but now this, if you have less values flow down something, then you are by definition going to have more stubborn mutants. So this is now stubborn as in not controlling for the location, right? And the reason for that is obvious because it's due to the reachability. If you have less values that flow somewhere, then statistically, if you toss your coin and you're trying to run down that branch of the code, then you have less chance of getting there because it's statistically harder to reach there. But this does not imply that you're going to have more really stubborn mutants where you actually control for the reachability. Right, so all this slide is trying to tell you is this problem of reachability might actually just get worse if you have larger programs. So if you were not worried about whether you can reach a mutant or not, for larger programs you should be even more worried whether you're going to reach the mutant or not. Okay, so the takeaway from this is if you do not have a precise oracle, then you shouldn't be in the business of testing anything. That should not be coming as a big surprise. If the goal is to create these stubborn or hard to kill mutants, then for example, for the relational ones, use only the off by one mutations. And that's great because it brings it down from 30 down to 4 possible mutations that you need to apply. And in general, the general rule is take mutations that make small changes to them.
So why is our goal only to create stubborn mutants?
Yeah,
Is the idea that we're going to use these to evaluate a test suite, and it's going to be a lot cheaper and give us a similar result if we just use the few stubborn ones? Is that your hypothesis?
My hypothesis is that if you are going to be using this as fault seeding, and you are seeding easy-to-kill faults, then it skews the results to make your tool look spectacularly good, but actually it was just because these things were easy to kill.
Well, that's only if you compute an absolute mutation kill score. And no one should ever use an absolute mutation kill score. You should only compare. I mean, so if you have some tool and you say its kill score is 90%, I don't care. I want to know, is that better or worse than some other technique? Because these should not be used. Absolute values should not be used.
Yeah, no, I agree with that, except that, of course, I mean, if you are going to be evaluating how good your thing is, then really just do not care about stuff that is going to be in the wash anyway. Like, all the tools are going to kill those ones, so just ignore it. It's better to just focus on the ones that are hard to kill.
Got it.
If you want to use all operators, one thing you can do is just simulate the program a few times, a few thousand times maybe, and record the locations that you reach, because those are obviously easy to reach because statistically they would be hit, and then don't do any mutations at that point. Okay, so that was the end of part one. Actually, that was not just part one, it was 90% at least. So don't worry, we're not going to be here all day. But this stuff that I'm going to show now is much more debatable. So get your guns out. This could be more fun. Okay, so work in progress. What I want to try and address here is something that has seen a lot of attention in the testing literature, and that is the link between coverage and whether there is some kind of connection between coverage and whether you actually find bugs or not. So what kind of fault detection capability does a certain coverage measure really have? And this might seem like a bizarre problem, but trust me, many trees have died in the quest to get to the answer of this one. Okay, nowadays it's USB sticks, I guess, but in the good old days, it was definitely trees that died. Okay, so not too surprisingly, we're going to make this assumption again that we don't know anything. This time it is actually a bit more contentious, because I think in real testing, testers actually do know something, and they often know a lot, but we'll get to that maybe a little later. Okay, but for now, just let's assume we don't know anything. And now we want to calculate the following thing. For a given program P, calculate the probability of achieving X% coverage with a test suite of size K. So you have a fixed size test suite, it's got K tests in it. What you want to know is what's the probability of getting a certain level of coverage. We could say 100%, say, branch coverage or something like that. So what's the probability of getting 100% branch coverage with, say, 5 tests in your test suite? That's one thing you want to calculate. The other thing you want to calculate is for a faulty program, calculate the probability of observing the bug with a test suite of size K. Because you have a bug in a program, you have K tests, what's the chance of you hitting that bug in the K test that you're going to be running? Now this one should come as no surprise. We already know how to do it because we can just use the stuff we've seen so far. This one is a little bit more tricky to see how we're going to calculate this one. Now here's how we're going to do it. We're going to use this thing called probabilistic symbolic execution, which is also the basis of what I showed you before, and I'll show it at the hand of an example. So here we have a little program. Takes x and y as input. What it's trying to return is x plus y, but it has a problem with that. The problem is if you take this first branch, which we're going to call the branch at 25, which is just the bytecode line at which that is, it's completely arbitrary, but 25. If you go in there, then you set a to 0, and then you return a plus y instead of x plus y, which would have given you the correct answer. So in some cases, this program is not going to calculate x plus y. But anyway, this is the code. So now we symbolically execute this, and we capture all the paths in the code, which in this case, there are only 4 paths. It's if you take the true branch here, and then true and false here, and similarly for the other branch. And this is encoded as at line 30, well, let's say at line 25, you take the true branch, so that would have been in here. And then at line 30, you take the true branch, which is this one. And then this last number is the probability of you taking that path, given that x and y is in the range of 0 to 9. So you can go and calculate that, but it is going to be 36% chance of taking that branch. So what we do is symbolically execute the whole thing. For every path, calculate the probability of that specific path, and record on every path which branches did you take. That's basically what's going on here. So if you want 100% coverage, you need to have a 30 true and false and a 25 true and false in your test suite. So obviously with one test you cannot get 100% coverage, 100% say branch coverage. But with two you can, right? Because you can pick this first one and the last one, and then you would have the coverage you want. Okay, so here's now how we do it. Well, let me actually show it back at the hand of example. It's maybe simpler. Here's your input. What you do is, let's say we only want test suites of size 2, and what we want is 100% coverage. What we do is we sample paths. We can actually calculate, in this case we can calculate it analytically, but the snag is just with that, if the program gets any bigger, like if it becomes 100 lines instead of like 10 lines, then unfortunately doing this analytically becomes a bit of a pain. So we sample to get the answer here. So we sample k paths m times. So here we want k equals 2, so we're looking for 2 tests. And we sample 1,000,000 2 tests. And we
what does k paths?
K is the size of the test suite.
The length of the path?
No, the size of test suite. So two tests.
Okay.
We're going to run this program twice, basically. That's what this is saying. Okay. So for a test suite of size 2, and what you want to obtain is 100% coverage. We pick 1,000,000 2 tests. So we pick 1,000,000 times two of these, but we base it on these numbers. So when we sample, we are more likely to sample this path than this path, right? It's just based on these numbers that we already calculated. If we do this for this example, we see that 230,000 of these cases we sampled will give us 100% coverage. Okay? And if you analytically calculate this, the answer is 23.04 or something. So the bottom line is, in this specific case, the sampling is pretty close to the analytically correct value. But bottom line is, the probability of getting full coverage or 100% coverage with 2 tests for this example is 23%. Right? And we calculated it here with this mechanism. Now, what's the odds of the bug? Let's say the spec is x plus y. If you look at the probability of the bug, it turns out it's 12 in 100. And it's going to be exactly in this case when you take the first branch on both ifs, and y is unequal to y plus x. Because if you take a equals 0, then this one returns y, whereas the spec says it should have returned x plus y. So that's the case in which it's different. Turns out if you do the model counting of this, it's 12 out of 100. So only 12 values is going to satisfy this constraint, basically. Now, how do you calculate the probability of the bug? So this little formula here. So the probability of seeing a bug is p. So what's the chance of not seeing the bug? It's 1 minus p. What's the chance of not seeing the bug? K times. It's 1 minus p to the k. So not seeing the bug is 1 minus p to the k. So seeing the bug is 1 minus that. Right? So if you do that, then you get the probability of the bug. As it turns out in this case, that is 22.6%. Now, where do you think I'm going with all of this, right? We had a 23% chance of getting the coverage, and we have a 22.6% chance of seeing the bug. Those two numbers seem kind of related, I would argue, which, by the way, is a complete accident because we didn't engineer this example to be that close in terms of the values. But anyway, so I'm going to argue that the real correlation between these kind of things is if the probability of finding a bug is about the same or higher than getting the coverage. Right? So if you have a low probability of getting the coverage, and you do get the coverage, then I'm going to argue that if there is a bug of a higher probability, then you would have probably found it when you've done your analysis. And if you did that empirically, you would say, okay, I've seen the bug every time I got the coverage, and you'd be a happy bunny, and you'd say there's correlation between whatever coverage you were looking for and finding bugs. All I'm saying is that's a complete accident because it all depends on what's the probability of these different things. And to try and back that up a little bit, I'm going to show you an example. So this is, again, my famous broken binary tree example. And what you see here is test suites of size 10, and each test includes 4 add and remove operations on the binary tree. So you either have 4 adds, 3 adds and a remove, 2 adds, 2 removes, whatever it is, but you have, that's what one test is, and you have 10 of them. Now, if you look at the the probability, let's say you want only 70% coverage. 70% coverage, you're going to be at about 100% chance of getting that at 5, it looks like. So after 5 tests, if your goal is only to reach 70% coverage, you have about 100% chance of getting it. If you want actual 100% coverage, which is this line here, you can see it's going to take you, well, even at 10, you're only at about a 60%, little less than 60% chance of actually getting that coverage. Now, here's the small problem. That bug I was talking about, that's where it's sitting, at 3% chance of finding it. So you can get 100% coverage in this example, and you're not actually going to get the bug, because these probabilities basically don't align here. So here I'm going to say, if you ran this, if this was your test that you were trying to evaluate, or your empirical setting, you'll probably find that you will argue here, no, these things are not correlated, because I got high coverage, I got the coverage I was looking for, I didn't find the bug, so this coverage is not as good at finding bugs. And that's because in this specific case, the probability was just much lower.
This is all statement coverage?
Well, here it was branch coverage, actually.
Okay, sorry.
I think I understand, and I have a couple, sort of canonical examples in my mind. Right? So the first is sometimes the probability of a bug might be very low, even if by branch coverage or statement coverage, it's easy to cover, because it's very value dependent. Right? Like, there's, you have to try it with, a prime number greater than 1,000,000 or something to do the wrong computation. And so then, that seems to fit the graph you showed here. Another one is, my one branch in the program is, did you guess the password correctly?
So that's the next example,
Okay, I'll let you go on that.
So I'm just literally showing you the opposite end of the spectrum. This is this broken binary tree triangle classification example, where it turns out the probability of the bug is sky high. And look at this branch here at the bottom. Like, even if size 10, you still have borderline 0% chance of getting it, because that for triangle classification, one of the tests that you need for full coverage is that you cover the case where all 3 sides of the triangle is the same, right? And the odds of that is remarkably low, and therefore to get branch coverage in this case is going to skew things here, because if you actually do get the branch coverage, you're going to be way down here. But I would argue in this case that although it's uncorrelated with high coverage, if you get the high coverage, means you have a very good chance of actually finding the bug, but because it just turns out that it's kind of somewhat artificial in this case. Now, this slide, I think, shows, if anything, the real problem we have here, because what is a real tester going to do? A real tester is not going to use this analytical framework I have here. A real tester is going to say, what does a triangle classification do? It's supposed to look at cases where the 3 sides are the same. Let's create a test like that. So actually, this thing that's way down here at the bottom, in reality, it's actually not down there, because a real tester would have created that test. Now, how does that change the equation, right? Basically, what that would mean is these things here at the bottom that now seems like to be low probability will actually move up in some sense. So you might actually now still get the case where you think there is no real correlation, because you just moved up the difficult cases, so they're no longer that difficult. So as I was saying, this is work in progress. I don't know where it's going to progress to, but all I really want to say is that probability of finding these things is actually the true link between them. And doing many more empirical studies here is either going to show you one or the other side of this equation, but not going to get you anywhere closer to the truth.
Well, I'm worried that the results might be dominated by what path the bug is on. I mean, there's there's paths that are easy to find via random testing and paths that are hard to find via random testing. And depending where the bugs came from, and folk wisdom that bugs are more likely to be on rarely executed paths, but rarely executed paths doesn't necessarily correlate with hard to find paths via this mechanism.
Yeah, but that the only case in which that is not going to be correlated is if the issue or the reason why it's hard to get is actually part of the oracle. If the oracle somehow narrows the branching, because otherwise, I mean, if the oracle is part of the if the oracle is part of the thing you're measuring branch coverage on, then by definition, there is no difference between finding the bug and finding the coverage, right? Because one of those branches says the assert returns false. And if you want to cover that branch, you can only cover it if you found a bug. So you must exclude the oracle out of this equation. Otherwise, it doesn't kind of hold. This is kind of the last slide because the next one, oh, well, actually, there is one more slide after this one. Well, anyway, this is still very preliminary, and I really don't know where this is going to head, maybe nowhere. It's maybe just some food for thought. And all these calculations are a bit expensive, especially this latter ones, and therefore it might only really work for small programs. But maybe there'll be some interesting insights in it. Now, some of the other stuff we're working on, the same framework I've just showed you, we can use that for probabilistic programming as well. So we have a little extension of our tool that can do probabilistic programming. It uses model counting as inference, so obviously it's only going to work in these cases where we can apply the model counting. There's some work on Monte Carlo tree search for worst case execution time. In the specific settings we were using it was working really well, better than just purely random and also better than reinforcement learning. There is one example I have that it doesn't work so well on, but I can tell you more about that if you want to know. And then recently I've been interested in more white box fuzzing, and the idea here is to try and come up with, if you don't know what the grammar is that's being accepted by a piece of code, maybe you can iteratively derive it, which is pretty much the goal of that work. And that is it.
We have time for a question or two. People have them.
So for the first bit of work that you talked to us about, where you learned all of these properties of like equivalent and stubborn mutants for these mutation operators, what does that actually tell us about these previous studies that use these mutation operators to evaluate their techniques, if anything?
Well, I can quote the other paper that was written on the ICSI thing, where basically they took a very diplomatic line and they said, like, these studies should maybe be revisited. Yeah, I mean, it probably doesn't invalidate necessarily all of them or anything like that. I mean, it's just a slightly different take on it, right? It basically just says, be a little careful when you do these kind of studies, because sometimes there are things that are influencing your results that might not be the ones you're really studying, right? And that's a classic problem of pretty much any data analysis-based thing, right? There might well be some other confounding variable that you're not considering. But yeah, I mean, my rule of thumb usually with all of these things is when I read the study and I go like, oh yeah, okay, now I can see why that is. Then I put the tick next to it. But if I do not see the obvious reason why this result is like it is, then I doubt it. So even without my work, that's usually my rule.
So what concrete things should people do to see whether they've forgotten some important factor?
I don't think I can answer that. Like I said, in my case, I have a rule when I do data analysis, and that's if it looks wrong, it is wrong. but that saved me a few times so far. But obviously, sometimes you do not have an intuition, right? And in that case, who knows? But sometimes, I mean, when you look at data and you were studying this one thing and it says, please only do your commits Wednesday night between 10 and 11 because that seems to be the case with the least bugs that gets introduced, then you probably should take that with a grain of salt.
Okay, great. Well, thanks very much. We appreciate it.